We can, yes, start our seminar. So hello, everybody. Welcome to today's Asian Pacific Analysis and PD seminar. Today, we are very happy to have a speaker from Lili Du from Sichuan University. Before the start, let me say a few words on Professor Lili Du. Professor Du got his PhD in 2005 from Sichuan University. Then he went to the south part of China, South China Technology University, and also Zhouping University as a postdoctor and also as a young faculty there. And until 2011 or 13, he came back as a professor at the Sichuan University. Lili is an expert on partial differential equations, in particular on differential equation and also equation from fluid dynamics. He has done many interesting work on free boundary value problems. So today he's going to give a talk on the Bernoulli-type free boundary problem and its applications. So without further delay, I will ask Lili to deliver his talk. So Lili, please.
Okay, thank you for Professor Xing. Thank you for the kind invitation by the organizers. It's my great honor to give a talk in Asia Pacific Analysis and PD seminar. The title of my talk is the Bernoulli-type free boundary problem and its application. Today, I would like to introduce the mathematics theory on the Bernoulli-type free boundary problem. And as a direct application, we establish the existence of the steady invasive rotational impacting J problem with gravity field. This is a joint work with my former PhD student, Zhen Fengchen, and Professor Zhouping in Chinese University of Hong Kong. What's a Bernoulli-type free boundary problem? It's a PD with free boundary. It's a free boundary problem with a transaction condition crossing the free boundary. We're giving a fixed domain omega, and ux is an unknown function. We assume that in the positive seat of u is a harmonic in the positive seat, and on the boundary of the omega, we impose the Dirichlet boundary conditions. U equals to g is a given smooth function, and on the free boundary on the free boundary gamma, we give the grading function of u. Lambda x is a given smooth function. Gamma is defined as the boundary of the positive C. So the Bernoulli-type free boundary problem means that we want to seek a solution, want to seek a harmonic function satisfying linear homogeneous Dirichlet boundary condition and inhomogeneous Neumann boundary conditions on the free boundary. Our example came from the Bernoulli's law and the constant pressure condition we will introduce in the following. In the study of the steady water wave and the Stokes wave. It should be noticed that because of the long trivial or in the grading crossing the free boundary, the optimal possible regularity is Lipschitz of the U. So the solve the Bernoulli-type problem, we will the weak solution of the Bernoulli-type problem, existence of the weak solution of the Bernoulli-type problem comes from the standard variational problem. We can define energy as this and admissible state as this. And so we can seek a minimizer of this functional and show the Lipschitz regularity of the solution. And we can show that U is subharmonic in the Hilbert domain omega in distributional things. We would like to refer the book by Luis Cafferini, Sasa, for the details. One of the most important problem is how about the regularity of the free boundary. For the case 1, if the given grading function lambda x is non-degenerate, that is, lambda x is larger than some positive constant lambda 0. For the Laplace equation, the linear case in 1981, Luis Cafferini shows that the free boundary is analytic. Very recently, we have shown that the same result for the semilinear case, U Laplace U equals to FU. U is given volatility function. One of the motivation to study the semilinear case is to investigate the incompressible jets with general volatility. Then, however, for the case 1, the degenerate case, if there exists point x0 on the free boundary, such that the grading of U vanishes at x0, then the natural question is regular or singular the free boundary near the degenerate point? The answer is singular due to the Hopf boundary due to the Hopf boundary point lemma. If the boundary is C1 smooth, Hopf lemma tells us that the normal derivatives cannot vanish at this point. In this talk, we only consider the non-degenerate case and use the mathematical theory to the well-posedness of the steady incompressible impinging jet flow. For the mathematical theory on the Bernoulli-type problem, we would like to point out the following books and the surveys by Eva Friedman, Alexo Figali, and some other bodies on the free boundary problem. As a direct application to the free Bernoulli-type free boundary problem, we investigate the steady incompressible impinging jet flows with gravity field. The physical problem is that consider the steady 2D free surface flow of inviscid and incompressible exotational flow emerging from a nozzle, a 2D nozzle, and falling under gravity. We assume the two-dimensional semi-infinity long nozzle. This is the inlet of the semi-infinity long nozzle in the far fields in the upstream, and A1, A2 is the orifice of the nozzle, and the N is the ground. The incompressible fluid impacts on the ground and formulates two free boundaries, gamma 1 and gamma 2, which evaluates at the A1, A2, the endpoints of the nozzle wall, and goes to two different downstreams in far fields. There are also many numerical results on the impinging jet flow problems. We don't mention them here. For the mathematical problem, the governing equation for the steady incompressible invasive flow is a steady incompressible oil system with the exotational condition. The diverging free condition, the conservation of momentum, and the exotational condition. U, the vector U is a velocity field, P is a pressure. G, the small g is the acceleration of gravity. Moreover, due to diverging free condition, we can introduce a scalar a stream function phi for the 2D plane flows and the 3D axially symmetric flows. Due to a rotational condition, the stream function psi satisfies Laplace equation for 2D case, and the linear elliptic equation for the 3D axially symmetric case. Moreover, we can obtain the Bernoulli's law for 2D case as follows: half of square of the speed plus the pressure and the gy equals to some constant denoted as B, the so-called Bernoulli constant. We would like to emphasize that the Bernoulli constant is unknown constant here. On the free boundary, we assume that the pressure satisfies the constant pressure condition. That means the pressure equals to the atmospheric pressure on the free boundary gamma. The atmospheric pressure is a given constant here. So we can obtain the following Bernoulli-type free boundary conditions for the 2D case and the 3D axially symmetric case. For the 2D case, gradient psi equals to this quantity. And for the 3D axially symmetric case, gradient psi over R equals to this one. For the mathematics theory on the well-posedness for the jets under gravity, to the best of my knowledge, there is only one result in the well-posedness theory due to Art, Cafferini, and Friedman in 1982. They considered two cases. The one is a 3D axially symmetric jet, and another one is 2D non-symmetric jet. They considered an incompressible invasive rotational flow falling from the semi-infinite long nozzle with infinite high in the far field, infinite high nozzle. They also point out that there are additional difficulties. The mathematical literature on jets with gravity is very meager. The reason is that the holograph method, which has been successful, used in steady 2D problem for jets and cavities without gravity, cannot be extended to the case where the gravity is present. So for the first case, the 3D axially symmetric nozzle with infinite high, they assume the nozzle wall in is a graph, and we can formulate the following Bernoulli-type free boundary problem. The stream function satisfies the linear elliptic equations in the fluid field, and on the axis we give the Dirichlet boundary condition, and on the nozzle wall we give this Dirichlet boundary conditions. And this is the Bernoulli-type free boundary conditions on the free boundary. The result by Art, Cafferini, and Friedman is as follows. For any given mass flux Q in the inlet in the upstream, there is a unique solution psi and gamma. Psi is the stream function, gamma is the free boundary to the jet flow jet problem with gravity. Moreover, there is a unique Bernoulli constant B such that the free boundary gamma initiates at the end point of the nozzle A. So furthermore, they also give the convergence rate of the free boundary approach to the axis. The key point of the result is that the Bernoulli constant B is regarded as a parameter to solve the J problem, and we can adjust the quantity of the B, the Bernoulli constant, such that the free boundary gamma connects the endpoint A. This is a perfect existence result for the axially symmetrical case. However, for the 2D case, on the other side, for the 2D non-symmetrical case, they also consider the related Bernoulli-type free boundary problem. However, there are two non-symmetric free boundaries, gamma 1 and gamma 2. In the fluid field, in 2D case, psi satisfies the Laplace equation with the Dirichlet boundary condition in solid ball, and on the free boundary, it satisfied the Bernoulli-type free boundary conditions. The result is that for any given mass flux Q in the upstream, there is a solution psi gamma 1, gamma 2 to the Bernoulli-type free boundary problems, which is satisfied as there is a unique constant, a Bernoulli constant B, such that the right free boundary gamma 1 initiates smoothly at the endpoint A1. However, maybe we don't know whether the free boundary gamma 2 connects the endpoint A or not. So a natural question is that can we find the mechanism to guarantee both continuous field conditions on A1 and A2? However, unfortunately, the three mathematicians give a counterexample and point out in general, one cannot fit continuously at both endpoints. In another word, they give a ill-positiveness result for the non-symmetrical jet. So can we establish a well-positiveness result for the non-symmetric jets with gravity with two continuous field conditions? One of the motivations is to modify the jet problem with gravity by Alt, Cafferini, and Friedman, and establish a well-positiveness result for the non-symmetric jet problem with finite height. So as an approximative model, we first investigate the following impinging jet problems. The aim of this work is to establish the well-positiveness theory on the incompressible impinging jet with two free boundaries issuing from the loader. The physical problem is that give out total mass flux Q in the inlet and atmospheric pressure P8m, the constant, thus there exists impinging jet under gravity with two continuous field conditions. The difference between the Cafferini problem and our problem is that in the inlet of the loader has infinite height in their problem, and however, the loader has finite height in our problem. We want to establish the well-positiveness theorem for the impinging jet problem with the finite height. Next, we will introduce the notations and assumptions on the loader. The ground N is the y-axis. We assume that the 2D loader wall N1, N2 are y-graph, and the C2 are alpha smooth, and they are flat. They are flat in the inlet, and the capital H is the distance between the orifice A1, A2 and the ground in. The width of the orifice is 2. In particular, the nozzle has finite height here. Our idea is that first we want to establish the Wilhelm's theorem on the impeding jet problems and take the ground to the infinity, take the ground in to the infinity and construct a solution of jet flow with gravity without the ground. Next, we denote Q be the total mass flux in the upstream. And the Q1 is the influent flux in negative x direction. Q1 is the influent flux in right. And the Q2 is the influent flux in right. Q1 is in left. As a simple fact, Q equals to Q1 plus Q2. However, in this work, Q is a given quantity in our problem, and Q1, Q2 are unknown a priori. Once we can determine one quantity, we can, and another quantity is fixed. Now we can define the solution to the impeding jet problem. A vector UVP, U is the horizontal velocity, V is the vertical velocity, P is the pressure, gamma 1 is the left free boundary, gamma 2 is the right free boundary. It's called a solution to the impeding jet problem, provided that the first condition is the free boundary gamma 1, gamma 2 can be described by C1 smooth functions K1, K2. Moreover, the free boundary are flat in the far field, and the asymptotic heights are H1, H2, respectively. The second one is the free boundary satisfies the continuous field condition 1. The condition 1 is the continuous field condition, and the smooth C1 smooth field conditions at the endpoint. This means that the free boundary connects to the endpoints A1 and A2 respectively. The third one is UVP velocity and pressure is C2 alpha smooth and continuous up to the boundary, which solves the steady incompressible Euler system with gravity field. The last one is the pressure P is equals to the atmospheric pressure on the free boundaries. As we mentioned before, the constant H1 and H2 are indeed the asymptotic width of the impeding jet in the left and right downstream. The property 1 in the definition implies the free boundary gamma 1 and gamma 2 cannot oscillate in the downstream. It's flat in the downstream. The condition 1 and condition 2 are so-called continuous field condition and smooth field condition for the impeding jet, which means that free boundary connect the reservoir smoothly. But the question is how to guarantee the continuous field condition mathematically. In recording the Bernoulli law, we can find that the Bernoulli constant is undetermined constant at the present stage. So we can treat two parameters, the Bernoulli constant and the influent flux in right or in left downstream as a parameter, a pair of parameters in solving the impeding jet problem, and show that there is a pair or parameters BQ1 to guarantee the continuous fit conditions. Hence, we treat. So the main result established here is the existence of the incompressible impinging jet with gravity as follows. For any given atmospheric pressure, PATM, and the total incoming flux Q is bigger than this quantity, we will explain the restrict in the next page. There is a solution UVP gamma 1, gamma 2 to the incompressible impinging jet problem with gravity. Moreover, the vertical velocity, we can show the vertical velocity is negative in the fluid field, and there is a unique smooth streamline gamma, the red line gamma, which separates the impinging jet with two different downstreams, and the gamma goes to the inlet of the nozzle and intersects the ground end at some unique point S. Moreover, the interface gamma is perpendicular to the ground. As a byproduct, we can show that the theorem 2, the asymptotic behavior of the impinging jet problem in downstream and upstream, and the theorem 2 gives that the velocity and the pressure converges to some uniform flow in the inlet and in the inlet and the downstream in the far fields. Next, we will explain the restrict condition on the total mass flux. The Q is bigger than this quantity, where G is the acceleration of gravity and capital H is the distance between the orifice and the ground. The condition 6 guarantees the following important facts in our proofs. It should be noted that the four quantities are B, Q1, and the asymptotic height, asymptotic width of the impinging jet H1 and H2 satisfy the relationship 7. The two equations with 4 parameters. So the condition 6 guarantees that the factor 1, this is the parameter B1, BQ1 can be determined uniquely by H1 and H2. On the other side, the asymptotic height H1 and H2 can be determined uniquely by B and Q1. The last fact is that the condition 6 also guarantees that the asymptotic height H1 is monotone increasing with respect to Q1, and the H2 is monotone decreasing with respect to Q1 for any fixed B and the total mass flux Q. So in this work, we have to restrict this condition on the total mass flux. However, unfortunately, the condition 6 prevents us to obtain the existence of the jet under gravity without the horizontal plane, without the ground end. We cannot take limit H goes to 0. On the other hand, this assumption also guarantees that this fact there does not exist the stagnation point in the fluid field, especially on the free boundary. The advantage of this fact lies in including the possible singularity on the free boundary of the water wave with gravity. The singularity of the free boundary flow with gravity is related to a very interesting problem, so-called Stokes conjecture. In 1880, G. Stokes conjecture that at any stagnation point, the free surface of the water wave, rotational water wave, has a symmetric corner of 2/3 of pi. The rigorous proof of the Stokes conjecture by geometry approach has been showed in the following famous paper. So the key assumption on the total mass flux helps us to exclude the possible stagnation point. Next, we will introduce the sketch of the proof of the main result. As we mentioned before, as a first step, we will formulate the following Bernoulli-type free boundary for the Bernoulli-type free boundary problem for the stream function psi. Psi is harmonic in the fluid field and satisfies the grading Bernoulli-type free boundary condition and the Dirichlet boundary condition on the solid wall. We denote lambda equals to B minus the atmospheric pressure. Here, we regard lambda as a parameter instead of the Bernoulli constant B. Once the lambda is determined, the constant B is fixed. The omega is possible fluid field. Omega 0 is a fluid field. Gamma 1, gamma 2 is a left free boundary and the right free boundary respectively. Gamma is the interface between the two fluids with different downstreams. As a first step to solve the impingement problem, we will solve the Bernoulli-type free boundary problem for any undetermined parameters lambda and Q1. And then we will show that there exists a suitable lambda and Q1 such that the continuous field condition is satisfied. However, the Bernoulli's law and the total mass flux condition gives a priori bound of the lambda and Q1. So in the following, we will solve the Bernoulli-type free boundary problem for any parameter in these restrictions. The step 3 is on the solvability of the Bernoulli-type free boundary problem. The solvability of the free boundary problem follows directly by the variational approach. We can define functional G psi and admissible state K. Psi satisfies the Dirichlet boundary conditions on the solid wall, and C can minimizer to the minimize the problem. Since the domain omega is unbounded, so the functional is unbounded for any psi belongs to the admissible state. We have to truncate the domain omega to the bounded bounded domain omega mu is defined as this. We truncate the domain with this additional boundary. So we will give some additional Dirichlet boundary conditions on the additional boundaries. Then if we establish the existence of the solution in truncated domain, this is a truncated domain, omega mu, and we can take the limit mu goes to the infinity, and to obtain the existence of the solution to the original impingement problem. So we first consider the truncated functional in the truncated functional in the truncated domain omega mu. Q1 and lambda is only parameter with these restrictions. Then the existence of the minimizer to the truncated problem follows from the standard variational measure. Due to the significant work we mentioned before by Art Louis Cafferini in 1981 to the Bernoulli-type free boundary problem, we can obtain the following important facts. Psi of the psi is harmonic function in fluid field. Moreover, psi belongs to Lipschitz class, and have the upper bound and lower bound. And moreover, the free boundary of the solution gamma 1, gamma 2 are analytic, and the Bernoulli-type free boundary condition is satisfied. Moreover, we consider the properties of the minimizer psi. First, we can obtain the following precise bounds 11 and 12. First, we can the bounds 11 and 12 gives us that the two free boundaries lies upon the asymptotic heights. Moreover, we can establish the monotonicity and the uniqueness of the minimizers. Especially, we can establish the monotonicity psi respect to the variable x. This fact implies that the vertical velocity is negative in the fluid field. Next, we will consider the property of the free boundaries in the truncated domain. The one important thing is the following non-oscillation lemma. The non-oscillation lemma implies that if we consider a part of free boundary, or this part of the free boundary, the width of the free boundary is less than c times height. So the facts gives us the continuity of the free boundary up to the endpoints A1 and A2. So we can define the initial point of the free boundary gamma 1 and gamma 2. So we can consider the key point, the continuous field conditions, and show that the free boundary connects the endpoints of the load. First, we establish the almost continuous field condition in the truncated domain, omega mu. The first condition means that the initial points of the gamma 1 lies on the left of the endpoint A1, and the initial points of gamma 2 lies on the right side of the A2. The second condition gives us that the one of the two continuous field conditions hold. The third and the fourth conditions give us if the Q1 is less than the total flux, then the right free boundary connect at the endpoint A2. If the Q1 is positive, the left free boundary connects the endpoint A1. This is almost the continuous field conditions. Next. Okay, we omit the details here. So next we will take the mu goes to the infinity and obtain the existence of the original impinging jet flow with almost continuous field conditions. Since we take the truncated parameter mu goes to the infinity, the free boundary may be break. The following facts may be occur. This below the wall. The free boundary, this is a truncated boundary. Maybe the free boundary is like that. So if we take the limit mu goes to the infinity, the free boundary may be break. So we will exclude the following two cases and show the continuity of the free boundary in the original domain omega. Finally, we will exclude the critical case Q1 and Q1 equals to 0 and Q1 equals to Q to obtain the continuous field condition. As recording the almost continuous field condition, we have that if as long as the critical case Q1 equals to 0 and the Q1 equals to Q are excluded, we can obtain the continuous field condition. So we will do this fact, we will show this fact in this step. So we will, in step 7, we exclude the critical case Q1 equal to 0 and Q1 equal to Q to obtain the continuous field conditions. For example, without loss of generality, assume Q1 equals to 0, we have to exclude the following three cases. The first one is that the left free boundary is close to the ground in the left far field. The second one is that the left free boundary is close to the ground in the right downstream. The third one is that the left free boundary touches some points x0 on the ground. We have to exclude the following three cases and show that Q is positive. Okay, finally, we will check the property of the interface gamma between the two fluids with different downstreams. Okay, I think my time is running out. I would like to stop here and omit the details of the proof. Thank you very much for your attention.
Okay, thank you very much, Lydia. So, well, very nice and interesting talk. And then, so now we have time for discussions. So, any question or comments from the audience? So we have enough time to entertain any questions or comments. Yeah, Tattoo, yeah, Professor McKenna, yes, please.
Can I ask, maybe your problem is stationary problem, some kind of evolution equation, maybe. What is the time evolution equation?
Evolution equation. This is a different. This is a very good problem, and I think we can. We first to study the steady problem first, and maybe we can investigate the evolution equations with more time. in the next in the future. Because there is no background solutions to this part of this work. The LOZO is arbitrary, and the free boundary is arbitrary. There is no smoothness of the in this case.
Thank you.
Thank you for your comment.
Sure.
Tattoo, I think, I mean, that if you want to study the time evolution, you have to have a right initial data. So this solution, this will be a starting point for your general initial boundary value problem. Yeah. So we know in which class we can set up the initial condition. Yeah.
So I think that the solution of stability of the solution given by you should be investigated to some evolution equation.
Yes, 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 you're right. Yeah, I think that's a interesting problem. Yeah.
Thank you.
So maybe it's a invested incompressible fluid equations, Stokes equation maybe.
Lili, can you make comments? Professor Makila asked me what happens to you to the compressible flows.
Oh, compressible flows. We can compressible flows. We have investigated the pure subsonic compressible flows and established the well-posed theorem in the 2 years ago.
Thank you.
Yeah, without gravity.
Thank you.
Yeah, Lili, can you illustrate a little bit why in the Caprari's original work, you know, this two-dimensional and symmetrical case, you cannot fit. You know, what is the key issue there, you know? Why the gravity make it impossible to fit?
Yeah. I think maybe the problem comes from they assume that the LOZO has the infinite height. You can think that if the LOZO is infinite with infinite height, the velocity may be brought up at the original or orifice. So we can establish some classical solutions for this problem. So we modified the model with a finite height.
So my question is, so their example depends crucially on this this LOZO has to be infinitely vertical.
I don't understand how to answer a question.
So you mean they give example shows you know, for this asymmetric two-dimensional case you cannot fit, right?
Yeah. Let me consider cylinder. The cylinder with infinite height, the velocity may be brought up at the orifice. So we cannot find the smooth solutions with the continuous field conditions in the downstreams.
Okay.
Thank you.
So, any other question? Let me ask one more question. So if the height h becomes infinity, then we will go bottom. So what's your conjecture? If there's no ground, you know, just so in that case.
My original idea is this is an approximated problem for the J problem. We have this first step to establish the well-postings for the impinging J. We can the second step is take the limit h goes to 0 and we can think the ground is disappear. So we can we want to establish the gravity or the jet with gravity. So unfortunately, we have to restrict these conditions. These conditions means the incoming mass plus Q is a finite number, and the H if goes to 0, okay, they cannot do this idea.
Okay.
The H has capital H has to have to upper bound probably.
Okay. Okay. Are there any other question, comments? So if not, then I think the time is up. Let's thank Professor Lili Du again for the very interesting talk. And then according to Daniel, everybody are welcome to have to go the coffee hour. Okay. Okay. Thank you all.
Thank you, Bruce. Thank you.
And the meeting details for the coffee break, but you should also have received them via email.
Okay. Okay. Yeah.
Thank you very much.
Thank you. I close the session.
Okay.
Bye.
Thank you. That's all. Yeah.
Thank you. Bye.